So in the last video, I taught you the word permutation, which is an ordering. And if you want to put things in order, it usually involves factorials for the reason we talked about. Okay, so let's talk about combinations. Combinations happen when you're selecting certain things, but you don't care what order you select them in. You just care what group of things do you finally end up with. So let's pretend still I've got 36 students, but I want to choose 3 students to give a gold star to for being pretty cool. But the order doesn't matter. If I choose Bob, Carlo, and Sally in that order and give them all gold stars, that's really the same as if I chose Sally, Bob, and Carlo and gave them gold stars. Because the order isn't important. I just care which group of 3 students are going to get the gold stars. So that would be an example where the order of the choosing doesn't matter. All that matters is what's my final group. Who's in my final group? So can we tackle this with fundamental counting principle? Not obviously, because the whole idea of the fundamental counting principle is I'm making my choices in some particular order. So if I tried to do it, I'd end up with the same answer as giving first and second and third place. It's like I'm going to choose one of my 36 students first, and then I've got 35 students left for the second choice, and I've got 34 students left for the third choice. But this way of counting is going to count Bill, Carlo, Sally as a different set of choices than Carlo, Sally, Bill, because I've made different choices for each. So the trick here is 36 times 35 times 34. That's going to tell me the total number of ways of choosing 3 students in some ordering where the order matters. What I want to do is I want to divide that by the number of ways I could reorder my 3 students after they're already chosen that are really the same. So for example, if I chose Sally, Bill, Carlo, that's the same as Sally, Carlo, Bill. That's the same as Bill, Sally, Carlo. That's the same as Bill, Carlo, Sally. That's the same as Carlo, Sally, Bill. That's the same as Carlo, Bill, Sally. So you can see that all 6 of these are the same students, just in different orders. And that's going to be true no matter which 3 students I chose. If I chose 3 other students, there's also going to be 6 different ways of putting them in an order. But I don't want to count each of these different ways as different. So for every group of 3 students, this number is going to count that same group 6 different times because you can put that same group in 6 different orderings. So if I just divide by 6, now I'm not counting all of those orderings. I'm only counting one of the orderings, which is all I really want because each ordering now corresponds to a unique group of 3 students. Since we're looking for patterns here, hopefully you know where the 6 came from. What if I just asked you how many ways are there to put 3 things in order? Aha. That's permutations. If I said how many ways to put 3 books on my shelf, you would have said 3 times 2 times 1 equals 6. And so here I was saying, how many ways can I put 3 students in order? The answer is 3 factorial, which is 6. So there's a shorthand notation for this type of situation where I've got a collection of things and I want to choose some number of them, but I don't care what the order is. I just care what's the final grouping. Here's what that looks like. Here I had 36 students, and I wanted to choose 3 of them. So you write it this way, 36, 3. It sort of looks like it's going to be a fraction. Like if I wrote a line there, that would be 36 divided by 3. But in this notation, you just write 36, 3. There is no line because it's not a fraction. It means something totally different. And you put parentheses. So this way of writing things means if there are 36 objects and I want to choose 3 of them, this refers to how many ways can you do that. So 36 choose 3, that's what we say. 36 choose 3 equals 36 times 35 times 34 divided by 3 factorial. Okay, what if I have, so Fremont High School, let's say it's got 2,000 students, and let's say we're going to choose 10 of them to be part of the principal's advisory committee. We're going to choose them at random. So how would you write that? Using this notation, I'd say I've got 2,000 things, people in this case, and I'm going to choose 10 of them. So this is 2,000, choose 10. And if you think about it in terms of a fundamental counting problem, I'm going to make 10 different choices. So there's 2,000 students for who's the first person on the committee. There's going to be 1,999 students for who's the second student in the committee. 1,998 students for the third person in the committee, and so on. So I'm going to make 10 choices here. But the order I choose doesn't matter, so I want to divide by the total number of orderings that each group of 10 is being counted for. Because remember, if I choose 10 people, this way of counting is going to choose all the different ways of ordering those 10 people as being different. So I want to divide by all of those orders that are really the same, which is all of them. So I'm going to divide by the number of ways to reorder 10 people. This is a very subtle idea. So if you're feeling like I sort of get it, but I kind of don't get it, stop the video, go back and rewatch the explanation for 3. Draw a little picture for yourself to try and make sense of it. Actually, here, I'll do it for you. Let's think about 4, choose 2. I've got 4 things, A, B, C, D. I'm going to choose 2 of them. I don't want the order to matter. So if you think about it as a fundamental counting problem, I've got 4 things I could choose for my first choice, and I've got 3 things I could choose for my second choice. And here I've listed all of them. So so if I choose A first, here are the 3 things I could have chose second, B, C, D. If I chose B first, I could have chosen A, C, D second. If I chose C first, I could have chosen A, B, D second. But look, if I choose A first and then B, that's the same as if I choose B first and then A. So I don't want to count these 2 possibilities as separate. And notice that no matter what collection of 2 I choose, let's do CB. CB is the same thing as BC. So these 2 I really want to count as just being 1. So that's what I'm saying is I want to divide by 2 because once I've made my choice of 2 things, there are 2 different possibilities that represent the 2 different ways I could have ordered my choices. And I'm dividing because I don't want to count those 2 as different. I just want to count one of them as different.